field or electrical field intensity. As we know, there is a gravitational field, and in the gravitational field, all the bodies are attracted towards the Earth. Similarly, we know that there is a magnetic field, and in the magnetic field, the magnets are attracted by the another magnet or repelled by the another magnet. So there is a attraction or repulsion in the case of magnet, and there is a attraction in the case of gravitational field. Now, if we are having a charge, then this charge will have its electrical field in the space around it. And if a charge, another charge which comes in the range of or near the charge, or we can say in the space of electrical field, then it will experience a force. And the force experienced by charge Q0, which is test charge, due to the electrical field of capital Q charge, will be equal to F will be equal to Q0 into E, where Q0 is the charge of test charge and E is the electrical field at this point due to the capital charge Q. Now electrical field or electrical field intensity, we can define it is the electrical force per unit charge. So if the charge is the force between the capital Q charge and Q0 charge is F, and Q0 is the test charge, then E is equal to F divided by Q0. Now since Q0 is also a charge, then this charge will also have its electrical field. Therefore, we want only the electrical field of capital Q charge. Therefore, the small Q0 charge should be very small. So, our definition will be electrical field will be equal to limit Q0 tends to 0, F vector divided by Q0. So, this will be the electrical field of charge Q, capital Q, at this point P. Now, electrical field is a vector quantity. Its direction will be from positive charge to its direction will be outward from the positive charge and towards the negative charge. The unit of electrical field intensity is Newton per Coulomb. We can find its dimension, and its dimensions will be equal to dimension of force M.l minus 2 divided by the dimension of charge A into T. This is equal to M.l T minus 3 A minus 1. Now we can find the value of F. F will be equal to 1 by 4 pi epsilon 0. F will be equal to 1 by 4 pi epsilon 0 into Q charge divided by R square into R cap into Q0, and so E will be equal to 1 by 4 pi epsilon 0 Q divided by R square into R cap, where R cap is unit vector in the direction of line joining the capital Q charge and small q charge. Now what are the electrical field lines? Now around the charge there are electrical field lines. Now electrical field lines are imaginary path which is subscribed by a unit positive charge which is free to move, and that path will be the field lines. Now there are many properties of field lines. One, the field lines will come out of positive charge and this will go towards the negative charge. Second property, the tangent to the field line is वापस the tangent इसको घटाना पड़ेगा. The tangent of field lines is the direction of electrical field. Two field lines never cut each another or never cross each another. The direction of electrical field lines is perpendicular to the conductor. The electrical field lines are never exist in the conductor. The density of electrical field lines is proportional to electrical field. Means if the density of electrical field lines is more, then electrical field will be more. And the last and important property of electrical field lines, that electrical field lines are not closed path, but the magnetic field lines are closed path. Means the electrical field lines will be either away from the charge or towards the charge. Now if we take the positive charge here, then the electrical field lines are going away from this and perpendicular to this. If we take the negative charge, then electrical field lines will come towards the negative charge. If two positive charges are placed near to each other, then the electrical field lines which are in between them, they are repelled and the curvatures will be there, and as shown in the diagram. If we take the one positive charge and another negative charge, then in between these two charges, the electrical field starts from positive and it will go to the negative in all the directions. One line, this line, second, third line, fourth line, all will start from positive charge and end at the negative charge. Whereas if the plate is positively charged, then the electrical field lines will be perpendicular to this, towards the right as well as towards the left. Now we will want to find the electrical field intensity due to a point charge on the axis. Now if capital Q charge is placed at A and Q0 charge is placed at point P at a distance R, then we have to find the electrical field of the charge Q at point P. Then first of all we will find the electrical force on the Q charge due to capital, on Q0 charge due to Q charge. That force will be equal to 1/4 by epsilon 0 epsilon R into Q into Q0 by R square into R cap. Here R cap is unit vector in the direction of line joining the capital Q, line joining the charges. Epsilon R is dielectric constant of the medium. Then electrical field, as we know that electrical field is force divided by Q0, which is the charge of a test charge. Then the electrical field will be equal to 1/4 by epsilon 0 epsilon R Q by R square into R cap. Now in the case if the medium is air, in that case epsilon R, or that is dielectric constant of air, is 1. Therefore the electrical field at the point P will be equal to 1/4 by epsilon 0 Q by R square into R cap. We can also write in the vector form. We can also find the electrical field intensity at the point, at any point. Now if Q, the charge, has its position vector R0 and the position vector at the point P where we want to find the electrical field intensity is R, then the distance between Q charge and point P is equal to R vector minus R0 vector. So the electrical field intensity, capital E will be equal to 1 bata 4 pi epsilon 0 Q divided by magnitude of R vector minus R0 vector का square into unit vector, or we can write this as a force will be, or we can write electrical field as 1 bata 4 pi epsilon 0 Q bata R cube into R vector, or we can write this as a 1 bata 4 pi epsilon 0 Q divided by magnitude of vector R minus R0 का cube multiplied by vector R minus R0. Proportion of electrical fields. If there is a system of charges and we have to find the resultant electrical field at a point, let Q1, Q2, Q3 dash 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 Q and R n charges and their electrical field at that point. E1 is due to Q charge, Q1 charge, E2 is due to Q2 charge, E3 is due to Q3 charge. Similarly, En due to M charge. Now, by the principle of superposition of vectors, we can find the resultant electrical field intensity using the superposition theorem. According to that, the resultant of vector quantity is vector sum of the vectors. So here we apply the same conditions here. The superposition of the electrical field will be equal to vector sum of E1 plus E2 plus E3 dash 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 En. That is equal to summation of n I is equal to 1 to n Ei vector. So in this way we can find the electrical field due to number of charges. If we take a specific case when the charges are 2, that is Q1 charge and Q2 charge, then the electrical field due to Q1 charge is E1 and due to Q2 charge is E2. Then the total electrical field due to Q1 and Q2 charge at a point P will be equal to E will be equal to E1 plus E2, where E1 is electrical field due to Q1 charge and E2 is electrical field due to Q2 charge. The direction of E1 charge is in OA direction and direction of E2 charge is in the OB direction. We can complete the parallelogram and the resultant is OR, which is equal to vector E vector is equal to E1 vector plus E2. The magnitude of this E vector will be equal to square root of E1 square plus E2 square plus 2 E1 E2 cos theta, where theta is angle between E1 and E2, that is BOA. The direction of electrical vector E will be in the direction OB, and the angle subtended by OB with OR is alpha. Then tan alpha will be equal to E2 sin theta divided by E1 plus E2 cos theta. So in this way we can find the resultant electrical field in magnitude as well in that direction. Now we will take the example for the electrical field. Now if we are having a two positive charge Q1 and Q2 charges, they are at a distance capital R from each another. Now we have to find the point which is on the line joining A and B, where total electrical field is equal to 0. Now since Q1 and Q2 charge both are positive charge, therefore the point P where electrical field is 0, it will be in between A and B. That is, this point is P and it is at a distance x from the A. Then at this point A, electrical field due to Q1 will be toward the right side and electrical field due to Q2 charge will be left side. So they are in opposite direction. So their sum will be equal to 0 when their magnitudes are equal. So the electrical field due to Q1 charge will be equal to 1 by 4 pi epsilon 0 Q1 divided by x square. This is equal to 1 by 4 pi epsilon 0 Q2 by r minus x square. So we can cancel 1 by 4 pi epsilon 0 and so r minus x square divided by x square will be equal to Q2 by Q1. By solving it, we can write x is equal to r divided by 1 plus square root of Q2 by Q1. Similarly, if we want to find the distance from the Q2 charge, then distance will be equal to r minus small x, and that will be equal to r divided by 1 plus the square root of Q1 by Q2 d square. Now if Q1 and Q2 charges are equal, then what is the position of P? Then Q1 and Q2 are equal, then x will be equal to r1 plus 1, that is r by 2. So if the two charges are equal in magnitude and of the same charge, then the point of equilibrium will be at the center. So electrical dipole, a combination of plus q charge and minus q charge at a very small distance constitute an electrical dipole. Electrical dipole moment, the product of magnitude of any charge of the dipole and distance between two charges is known as electrical dipole moment. Electrical dipole moment is a vector quantity. Therefore, P vector, which is equal to Q into D vector. So, here D is a vector joining negative charge minus Q to positive charge. The line joining positive charge and negative charge is known as axis, and the direction of dipole moment P is from minus charge Q to plus Q charge, that is A to B, and this is known as the axis of the dipole. An axis which is perpendicular to the axis of the dipole and passing through the midpoint between the two charges is known as equilateral axis. The unit of dipole moment is coulomb into meter. Now, how to explain the electrical dipole or physical explanation of dipole, electrical dipole. Now, we know that an atom consists of nucleus with positive charge and electrons are circulated around the nucleus. The charge of proton is positive and charge of electron is negative. In the normal atom, the center of mass of positive charge, that is proton, and center of mass of negative charge, that is electron, coincide at a point. Hence, the dipole moment of such atom is 0, or we can say such atom is non-polar atom. Now if we put this atom in external electric field, then the center of mass of proton or positive charge and center of mass of electron, that is negative charge, they are displaced. So there is a distance between the center of positive charge and center of negative charge, and this distance is d. So now this atom, which is in the presence of electrical field, is a polar molecule and its dipole moment is q multiplied by d vector. Now similarly in the case of molecules, if we take the molecules of hydrogen H2, then the positive charge is towards right for the left H and left of the diamond. So the dipole moment for H is P1 towards right and next H is P1 towards the left. So net dipole moment is 0. So H2 is non-polar molecule. Now if we take the case of water molecule contains H2O, one H, another H and O. The negative charge center is here, positive charge is here and here. So dipole moment for OH is P1 this side, OH is P1 this side. The angle between these two P is 105. Hence the resultant of these two P1 and P1 is this one. So it will have a dipole moment. So the water molecule has permanent dipole moment, or we can say it is a polar molecule. Now we will find the electrical field on the axis of a electrical dipole. Now we consider a dipole whose minus charge is at A and plus Q charge is at B. The distance between center of the dipole and the P point on the axis where we want to find the electrical field is capital R. The distance between A and O is equal to distance between O and B, which is equal to d by 2. So the electrical field at point P due to negative charge will be vector E minus Q. This will be equal to 1 by 4 pi epsilon 0 minus Q divided by R plus d by 2 का whole square. Similarly, the electrical field due to positive charge at B will be equal to E plus Q vector. This is equal to 1 by 4 pi epsilon 0 Q divided by R minus d by 2 का whole square. The direction of both is in the direction of P. So total electrical field at point P will be equal to sum of these two fields. So E will be equal to Q divided by 4 pi epsilon 0 1 divided by R minus d by 2 का whole square minus 1 बटा R plus d by 2 का whole square. So E vector will be equal to twice R into Q into D into P vector, P unit vector divided by R square minus D square बटा 4 का whole square. So this will be equal to twice R into P vector divided by R square minus D square बटा 4 का whole square. Since Q into D into P unit vector is dipole moment P vector. Since capital R is much greater than d by 2, therefore we can write R square minus D square bata 4 square is equal to R square. Hence electrical field on the axis will be equal to 2 into P vector divided by R2. This is equation number 1. Now we will find the electrical field of electrical dipole on the equatorial plane. Now we consider the minus Q charge at B plus Q charge at A. The distance between O and A is d by 2 and O and B is also d by 2. We consider a point P which is at a distance smaller ले लो L. Now the AP and BP are equal and that is equal to be smaller. Now what will be the electrical field at point Q to the positive charge at P? This will be equal to 1 bata 4 pi epsilon 0 Q bata L square multiplied and its direction is AP, this direction. Similarly, the electrical field due to negative charge will be 1 bata 4 pi epsilon 0 Q into L Q divided by L square into the direction will be in the PA direction because the charge at B is minus Q. So the electrical field EA in the AP direction and PB in the PB direction. So we will resolve this vector in the horizontal and vertical axis. If theta is the angle between PAB and PBA, so this angle will be also theta, this angle will be also theta. So the component of EA in the direction of horizontal axis will be EA cos theta and in the vertical axis is EB
sin theta.
EA होगा EA sin theta.
Marker होगा.
Similarly, the horizontal component of EB will be EB cos theta in the horizontal axis and EB sin theta in the vertical axis. Since EA sin theta is equal to EB sin theta, but they are in equal and opposite direction, so they cancel. So only electrical field will be in the horizontal direction and its value will be equal to EA cos theta plus EB cos theta. So resultant electrical field will be in this direction, which is in the direction of A to B and which is opposite to the direction of dipole moment. Now total electrical field will be equal to EA cos theta plus EB cos theta, that is equal to 2 EB cos theta, since magnitude of EB and EA is equal and we can put the value of cos theta. So electrical field will be equal to 1 bata 4 pi epsilon 0 Q into D bata LQ, because cos theta is equal to D by 2 bata L. Cos theta will be equal to D by 2 divided by L. So the total electrical field will be equal to 1 bata 4 pi epsilon 0 Q into D minus P vector divided by LQ. Now we can find the value LQ. LQ will be equal to OP distance is R. So by the Pythagoras theorem, PB is equal to D square bata 4 plus R square. So substituting this value, we will get E is equal to 1 bata 4 pi epsilon 0 minus P divided by L square plus D square bata 4 ka power 3 by 2. And since D is much lesser than R, so we can write electrical field will be equal to 1 bata 4 by epsilon 0 P divided by R cube. So here we see that we compare this equation number 2. We compare equation number 1 and 2. Then it shows clearly that electrical field on the axis is twice in magnitude of the electrical field or the electrical field. Second thing, the electrical field on axis or electrical field on electrical field is directly proportional to P. It means the electrical field at axis and equatorial plane will not depend only on Q and D, but it will depend on the product Q into D, which is dipole moment. The direction of electrical field, on the axis is in opposite direction to the direction of electrical field due to dipole in the equatorial plane. So this completes the dipole.